Hello and welcome. Much of what we've been doing in this class up until now has involved the use of equations. Equations are a wonderful, compact, and even elegant way of describing and manipulating patterns between quantitative things. The relationships between cost and quantity and total price, the relations between force and mass and acceleration, the relation between velocity and distance and time. These are things that are intimately connected with each other in ways that we can describe by using equations. And we can show that in that form. We can also show it in a very visual form by graphing them. And that's exactly what we're going to be focusing on today. So first off, let's take some time for ourselves here to empty our mind of thoughts so that we can sort of clear the screen in front of us, so to speak, as a way of making it so that we can completely focus and be here right now in the moment, ready to completely focus our attention on what we are about to discuss together. So take some time to do that. Welcome back. Well, describing data visually, describing quantitative information visually is nothing new actually within our class. We have created line graphs, we've created pie charts, we've created bar charts, we've created histograms of data in some of our previous discussions together. And in addition to that, we've sometimes described numbers in terms of this basic number line that goes back and forth, with numbers on the left being very negative, numbers on the right being positive. And we will make use of that exact same number line here, shown directly above my head here. But since we are now dealing with relationships between that involve not just one quantity, but relationships that are between two different quantities, now we're starting to need not just one axis to describe this information, but to also need a second axis, a second number line. This time it's turned vertically with negative values near the bottom and positive values near the top here. And instead of just marking each one of those number lines off like a ruler in one direction, now we're marking both of those number lines also like rulers, so that we eventually actually create this sort of square grid in which we can plot various points. There's some vocabulary that we will make use of as we're making use of this coordinate system. We call this a Cartesian coordinate system. Cartesian is an odd way in which we reference the mathematician, the French mathematician who was the first one to try and do this. His name was Descartes. First name René, last name Descartes, one of the earlier French mathematicians and philosophers who said, "I think, therefore I am." This is the person whom we credit to this. So it is a Cartesian coordinate system credited to René Descartes. And as you can see here at the center of this particular Cartesian coordinate system here, at a place where both of the rulers are at 0, we call that place the origin. And you can see that the two axes really divide this section into 4 portions to it, and I'll get to that in a moment here. But let's describe what we first of all call this horizontal number line here. We call that the x-axis. Similarly, as you might know, the one that goes in the vertical direction is not the x-axis, it is a y-axis. So the x-axis and the y-axis, describing this two-dimensional realm here in which we work. And so in the area in which both x and y are, in which both the horizontal ruler is positive, is into positive numbers, and the vertical ruler is also into positive numbers, we call that quadrant 1. As we take a look at quadrant 2, where are we on the horizontal ruler? Are we in the positive area or are we into the negative area? Well, I see a lot of negative numbers below that sign that says quadrant 2, showing me that for the x-axis we're looking at negative numbers. We're still in the upper portion of the Cartesian coordinate system here, and so those y values on the vertical ruler are actually still positive. So x values are negative, y values are positive in quadrant 2. If we continue this rotation into the other two quadrants here, quadrant 3, you can see that in quadrant 3 both rulers are actually into negative numbers. Both the x value is negative and the y value is negative. And lastly, for quadrant 4, we are back to positive numbers on the x-axis but still into negative values for the y-axis. And this reminds me of a game that I used to play as a child. This is a game called Battleship, in which you would secretly place various battleships in certain locations on a grid, and you would also on a grid that's directly in front of that you can actually see, you would blindly start firing bombs at locations that you hope contained your partner's, your opponent's ships, and essentially it was to try and knock out your opponent's ships before your opponent does the same thing to you. And the way in which you would reference a given location on that grid was on the left-hand side. You can see A, B, C, D, E, F, G, H, I, J, and similarly across the top you can see a series of numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so by saying D7, you referenced a specific location in which you were firing a missile, and your opponent could see whether or not there was a ship in that location and say either hit or miss.
H7. Hit. B6. Miss. H8. Hit. C5.
Battleship, a great game of strategy, action, and suspense.
Miss. H6. You sank my battleship.
The game you can play anywhere. Battleship, from Milton Bradley.
In the same way, we can take a look at this Cartesian coordinate system in much the same way, except we are not making use of letters for one of the axes. We're using numbers for both axes here. But in the same way, we are making use of two numbers in order to define a specific location. Instead of saying E7, we're saying 4, 5. So take a look first at the x-axis here, because that's where the first number goes. 4 is the first number in that first ordered pair there. We call these things ordered pairs. The number 4 there references a location on this horizontal x-axis there. So find the number 4 there, and then find the location on the y-axis that corresponds to the number 5, and plot a point at that location. So predict where this point is going to show up here. Point 4, 5 shows up right here. Did you get it right? Take a look at the next one. -4, -5. So find that location on the graph here someplace, and hopefully your prediction is correct here. -4, -5. Remember, the first number is the horizontal direction. The first number corresponds to the x-axis, not the y-axis. -1, +3. Take a look at that and predict where it's going to be. 3, -1. Take a look at that one and see where that's going to be. Interestingly enough, those two ordered pairs, -1 and 3, and 3, -1, correspond to very different locations on the grid, don't they? The order matters when you're dealing with ordered pairs. Take a look at the next one. 1/2 and -7/3. Well, that's kind of inconvenient. -7/3, that's about 2 1/3. Okay, so that's somewhere between -2 and -3. See where that's going to show up here and sort of eyeball it. Predict where that's going to be located. All right, so hopefully that's consistent with the place that you were looking. -2, 0. -2, 0. See where that's going to be. All right, now notice that when the y-coordinate is 0, that places us on one of the axes. It places us on the x-axis. When the y-coordinate is 0, that places us on the x-axis. Similarly, when the x-coordinate is 0, that places us on the y-axis. That's something that's important to remember, and it seems a bit backwards, doesn't it? The y-coordinate being 0 is going to place us on the x-axis, and the x-coordinate being 0 is going to place us on the y-axis. And we actually have names for such points. When a point sits on the x-axis, we call it an x-intercept. When a point sits on the y-axis, we call it, you guessed it, the y-intercept. Here's the next one, 0, 0. Hopefully that one's pretty easy. Take a look at where you think that point's going to show up. There it is. It's right there at the, what is it called? The origin. And lastly, we have the point pi 1.1. We can plot irrational numbers on here all we want. We just have to sort of eyeball where they're going to go. So 3.14 and 1.1. Take a look at the location where you expect it to be and see if you're right. Very good. So hopefully that's straightforward to you. You can see how these things work, and we can take some time to actually go in the opposite direction here. I'm not sure what that 4, 5 is doing there. That shouldn't be there, but let's take a look at the 4 points that are sitting on the Cartesian coordinate system here, and let's ask, what are the coordinates of point A? Well, let's take a look here for point A. It looks like it's -1 in the x direction. Remember, x direction is first. -1 in the x direction, and we have to go down 3, down to -3 for the y direction. So -1, -3. There we are. For point B, we're also in the negative x direction there for so -2, but this time we're going up into the positive y area here, which is +3. So -2, +3. For point C, both of those coordinates should be positive. Looks like we're going to estimate it here at 3.5 and 1.5. So 3.5 in the x direction and 1.5 in the y direction. And lastly, for point D, that's still positive in the x direction at about 1.5, and it's negative now in the y direction at -2. All right, so take some time with this. Take those ordered pairs that you see in front of you and plot those points onto the associated Cartesian coordinate system that I've provided for you on your activity sheet. Take some time to do that. Welcome back. Well, we have points extending into all 4 quadrants of our Cartesian coordinate system here. The first one is point 3, 4, which you can see plotted up there in quadrant 1. -2, 2, that ordered pair is plotted up as point B in quadrant 2. 4, 0, which axis is that going to be on? Yes, the x-axis, since the y value is 0. So that's point C there, shown on the x-axis in the positive area of the x-axis. The next one, 5/2 and -1/2, that's point D, that's in quadrant 4. And lastly, you can see -5, -2, shown up there as point E, that's in quadrant 3. Alright, so in similar fashion, let's take the points that you're seeing on this Cartesian grid and let's try to find the coordinates of each one of these points. Take some time to do that. Welcome back. Well, those ordered pairs there are intended to be provided in order going down 2 columns there, going from point A to point H. So our first point there is -7, 0. It's sitting on the x-axis. -5, 4, well, that's point B that's sitting in quadrant 2. 0, 6, that's a y-intercept that's sitting well, on point 6 of the y-axis. 0, 0, that's D, that's at the origin. -1, -2, that's point E, sitting in quadrant 3. 2, -6, that's point F, that's in quadrant 4. Point 6, 1, that's point G, that's in quadrant 1. And lastly, point 6, -1, that's point H, that's also sitting in quadrant 4. So we can sometimes use these kinds of ordered pairs as means of telling a story. We've already seen this in some of our adventures with line graphs, where plotting things in 2 different dimensions allows us to tell a story. In this case, I'm showing you hours after midnight in the first column of information there. And in the second column, I'm showing you temperatures in degrees Fahrenheit. This is a very, very cold night. So hours after midnight, for 1 hour after midnight, that's 1 a.m. At 1 a.m., the temperature is apparently 2 degrees Fahrenheit. At 2 a.m., the temperature is 0. At 3 a.m., we're now 1 below 0. At 4 a.m., we are 2 below 0. At 5 a.m., we are -4. And lastly, at 6 o'clock and 7 o'clock, when the sun starts to come out, the temperature starts to rise here. We see the temperature reverse to +1 and then +3. Well, if we plot this on the Cartesian coordinate system here by creating some ordered pairs from each one of those data combinations, then we can see the story playing out from left to right here. Starting at 1 a.m., the temperature gets colder and colder and colder. You can see that sloping downward, and then suddenly sloping back up again as the temperature starts to warm up in the morning. Here's another application here, and I'm going to introduce this here and actually not come back to it until later on in our video together. Here's an application of linear equations here that I think you'll find to be pretty fascinating. Let's say that there's an internet access company that you're wanting to sign up for, and it offers 3 different data plans. Now, the first plan is, in some ways, the cheapest in that it's only $50 a month, but it charges you for each gigabyte that you download, and it charges you 10 cents for each one of those gigabytes that you download. Plan B is $100 a month, but the charge per gigabyte is only 4 cents, for each gigabyte that you download. And Plan C is $200 regardless of how much you download. Well, which one is the best plan for different customers? Well, you might be able to take a look at this and say, well, if you are not using the internet very much at all, you're just checking email every now and then, and that's about it, you probably want to go with just Plan A, because your downloads are going to be very, very minimal, and so that your cost is going to be pretty low at just $50 a month. However, if you manage 3 YouTube channels that all involve you playing World of Warcraft while posting online to your Facebook feed, then you're probably going to want to make use of Plan C, which is the flat fee of $200 a month, because paying 10 cents for each one of those gigabytes will add up very quickly. So this is an example of an application in which we've got 2 different variables that are in relationship to each other. In fact, there's one relationship for each one of those plans. Plan A has a relationship between data usage in gigabytes and the monthly fee in dollars. Plan B has a different relationship between those 2 variables, and Plan C has a different relationship still. And so how do we make use and explore, how do we make use of some of the tools that I'm going to be showing you today to explore which of those data plans is best for different customers? Well, we'll do that later on here, but first let's talk about how we might take some of these relationships between quantities and place them in a visual format using the Cartesian coordinate system. Let's start here with x plus y equals 4. That's a relationship between variables here. The variables are x and y, and the way in which we could try and discern what that relationship is to try some values for x and for y and see what the other value has to be if I plug in a certain value for one of the variables. Here's what I mean. Let's say, for example, for x, I try to just plug in the value 0. I then solve that equation for y to find out what the solution is for y. Well, if x is equal to 0, that means 0 plus y equals 4. Well, what's the value of y then? Y has to be 4. So we can see there that there's a relationship between x and y, and we can see that reflected in this case scenario here, where x is equal to 0 and y is equal to 4. So we can tease out the relationship a little bit further by trying some other values. If I plug in 1 for x, that's 1 plus y equals 4. Well, what's the value of y? It's got to be 3. And you can see that for each one of these pairs of numbers here, x and y, I forgot to mention this, but you can see that there is a point that we can make on the Cartesian coordinate system. A point that has a value x of 0 and a value 4 for y. 0, 4, that's a y-intercept that's sitting in the upper portion of the y-axis there. In the same way, we have another point here that's 1, 3, so 1 in the x direction, 3 in the y direction. Where's that point going to show up? See if you can see where it's going to be. See if you're right. It's right there. Let's do a few more points here to fully tease out this relationship. If I plug in 2 for x, what's y going to be? Well, we'll have 2 plus y equals 4. All right, so the value of y that makes that equation true is 2. So 2 comma 2 is another solution to this equation, and we can plot that there. If I plug in 3 for x, we have 3 plus y equals 4. The value for y has to be 1. So 3 comma 1, I plot that right there. And lastly, if I plug in 4 for x, we have 4 plus y equals 4. Well, the only value of y that makes that a true statement would be 0. So I can plot that there as well. That's an x-intercept. It's hitting the x-axis, which is evidenced by the fact that the y value is 0. Well, what's the overall pattern in here? I've obviously not plugged in every possible value here that I could plug in for x, but what do you think I would get if I were to plug in 1/2 or 2 3/4 or 3 1/2 or 7 or 12 or something like that? Where would those points show up? What's the overall pattern here? Well, perhaps you can see that the pattern that is beginning to become visible is that all of these points that are solutions to that equation will show up on this line that follows in this direction here. That line is the set of all points that are solutions to that equation there. So in many ways, we're starting to talk about solutions of equations, and we've done this before here. It's always been equations that just have one variable here. So I'm showing you an equation here that's complex, but it only involves one variable here. So if I look at this particular equation here, and I ask, is x equals 1 a solution? How do I find that out? Well, I plug in 1 for x to see if I suddenly get a true statement. All right, so I'm going to plug in 1 for x there, so it's now 1 minus 2 plus 5 times 1 is equal to 4. All right, let's see if that's true. Well, 1 minus 2 is, 1 minus 2 plus 5 times 1, remember, order of operations, I have to do that multiplication first. 5 times 1 is just 5, and so then I have 1 minus 2 plus 5 equals 4. Well, that is in fact true, that 1 minus 2 is -1 plus 5 is +4. So yes, 4 equals 4. This is a true statement, and so x equals 1 is a solution to that equation. In the same way, we're finding solutions to equations that have two variables by we can plug in values for x and y to see if we get a true statement. So for example, let's try 2, 0 to see if that's a solution to that equation. We plug in 2 for x, we plug in 0 for y, and we see if the statement's true here. All right, so 6 times 2 minus 5 times 0 is equal to 12. Question mark, we're not really sure, but 6 times 2 is equal to 12, 5 times 0 is equal to 0. We have 12 minus 0 equals 12, which is the same thing as 12 equals 12. Yes, that point, that ordered pair there of 2, 0 is a solution to that two-variable equation up top. Let's try it with 3, 1 here. We'll plug in 3 for x and 1 for y to see if we get a true statement here. We're getting 18 minus 5 is equal to 12. Well, in this case, 18 minus 5, that's 13, not 12. So we have 13 equals 12. That's not a true statement. So 3, 1 is not a solution to that equation. Well, lastly, let's try the one that's above me here, 1 and -6/5 here. Let's plug those things in here. You can probably see why I chose -6/5 here, because when I multiply that times 5, some things are going to cancel out. Those two 5s are going to cancel, leaving us with just 6, and the fact that it's a -6 multiplied by that other minus there, so a -5 times -6/5, that's going to be a +6. So 6 plus 6 is equal to 12. That's true. So 1 and -6/5 is a solution to the equation up top. Let's actually do some work along those lines yourself there. See if each one of these points is a solution to that equation on top. Take some time for that. Welcome back. Well, this was very similar to the set of problems we did on the previous slide here. Negative 4 comma 0, we're testing to see if that's a solution to the equation 3x minus 2y is equal to negative 12. So we plug in 4 for x and 0 for y, and so we have 3 times 4 minus 2 times 0 is equal to negative 12, question mark. We'll see if that's true here. So we have 12 minus 0 equals negative 12. That's if we do those two separate multiplications there. And then we have 12 is equal to negative 12. Not true. That's not a true statement. So 4 comma 0 is not a solution to that equation. Similarly, negative 2, 3, we'll test that out as a solution here. So 3 times negative 2 minus 2 times 3, that's negative 6 times, or negative 6 minus 6. That turns out to be negative 12, which is the same thing as, of course, negative 12. That is a true statement. So negative 2 comma 3 is a solution to that equation. Lastly, if we plug in 1 and 15 halves, that's 7½ basically, into that equation, let's see what happens here. We have 3 times 1 minus 2 times 15 halves is equal to negative 12. Well, doing those two multiplications gives us 3 minus 15 is equal to negative 12, and 3 minus 15 is in fact negative 12. So yes, that point is another solution to that equation. And hopefully you're starting to see the point here that if I were to plot all of the points that turned out to be solutions to that equation above, they would all form a straight line. And we're going to show more of that in the next few slides to come. For example, this one right here. X minus 2y is equal to 8. Let's just try some values here for x and for y. So let's plug in 2 and 6 and 0 here for x. You can try whatever values you want. You can try negative 10, you can try 140, you can try square root of pi, whatever you want to try. But I'm trying here some ones that are pretty easy and straightforward in terms of their the algebra that's involved in finding y. So if I plug in 2 for x here, I get 2 minus 2y is equal to 8. So okay, I'm going to be subtracting 2 from both sides, and I'll have negative 2y is equal to 6. Then I divide both sides of the equation by negative 2, and I get y is equal to negative 3. All right, so hopefully that language that I gave there made some sense. And 2 comma negative 3, where would I plot that? Remember, the x direction is horizontal, and we do that one first. 2 comma negative 3, see where the point's going to be, and see if you're right. Let's plug in 6 now. If we plug in 6 for x, we have 6 minus 2y is equal to 8. Now we're subtracting 6 from both sides, and we have negative 2y is equal to positive 2. And so when we divide both sides by negative 2, we get y equals negative 1. 6 comma negative 1, see where that point is going to be, predict where it is, and see if you're right. All right, here's one more here. If I plug in 0 for x, well, that x term is going to just drop out, and I have minus 2y is equal to 8. So again, I'm dividing both sides of the equation by negative 2, and I get y is equal to negative 4. So it looks like I'm going to have a y-intercept of negative 4. You can see there that those 3 points are forming a straight line. And it's usually, although sometimes I'll be asking you to just plot a line based upon 2 points, oftentimes 3 points can be the best way of doing it, because the third point can serve as a check to make sure that you have 3 points that all confirm that they're lined up in the same line. Like when you're creating a line in carpentry, you want to mark off 3 different points of that line just to make sure that you're consistent and haven't made a mistake somewhere. So there's our line. If we were to try every single possible value for x and find out what every single possible value for y is, we plot all those points, and each point would be somewhere on that blue line, going in opposite directions. Remember, as we defined in as we're about to define in geometry pretty soon here, we're going to be showing that a line goes infinitely in one direction and infinitely in the other direction. It's got zero thickness, but it extends in both directions infinitely. And you can see an example of that here. These lines, this line does not end. It goes on and goes on and on and on in both directions. All right, so do this one here. Graph 2x plus y equals 6. Again, you can choose whatever values of x that you like, so your results might look a little different from mine. However, your line should look exactly like the one that I come up with. Take some time for that. Welcome back. Well, again, the values of x and y that you came up with might be different ones than I chose here. Similarly, the points that you plot might be different points from the ones that I plotted, but your line should match mine. It should be a line that intersects the y-axis at positive 6 and which intersects the, well, appears to intersect the x-axis at positive 3 there. So it's sloping downwards. And as you can see, it goes through, at least from my results here, the point negative 2, comma 10, 0, comma 6, and 2, comma 2. Let's just do some more practice here. This is a slightly more complex equation here, just more scary numbers. 4x plus 3y is equal to 15. Well, what are some numbers that I can try for x here? 0 and 15/4 and 3. Well, you're going to see actually in a moment here that what I'm doing with the 15/4 is actually something that's pretty strategic. Let's first of all try plugging in 0 for x. If I plug in 0 for x, then 4x goes away. That term just becomes 0. So I just have 3y is equal to 15. I divide both sides by 3, and I get y is equal to 5. In the same way, let's actually try plugging in 0 for y and see what happens there. Well, if I plug in 0 for y, now the 3y term turns to 0 and just drops out, and all I've got left is 4x is equal to 15. Well, I have to divide both sides of the equation by 4, and I get x is equal to 15/4. It's kind of an ugly fraction, but nonetheless, there it is. Lastly, let's do a third number here, which is x equal to 3. If I plug in x is equal to 3, then 4x becomes 12. So I have 12 plus 3y is equal to 15. I subtract 12 from both sides. I get 3y is equal to 3. I divide both sides by 3, and I get y is equal to 1. And if I plot that point, it looks like it's right here. So it looks like we're doing pretty well here as far as no mistakes is concerned. Those 3 points seem to line up in a nice line right there, like that. So you can see here from this one that you can try plugging in 0 for x. You can also try plugging in 0 for y, or any other value for y for that matter, and see what the corresponding x value is going to be. So you can do this from both sides of that table on the far left there, which I tend to call a t-table. So do this one here, 2x plus 3y equals 12. Plot some points based upon some values of x and y that you determine from that t-table on the far left, and plot what you get in the on the Cartesian coordinate system there. Take some time for that. Welcome back. Well, you can see here once again I plugged in values of 0 for x and y. Again, you can plug in whatever values that you want for x or for y, but from my perspective I may as well make it easy. So I'll plug in 0 for x and I get a y value of 4. In the same way, if I plug in a 0 value for y, I get 6 for x. And lastly, just as a check, I plugged in a third value of x for 3, and I got a y value of 2. So plotting those 3 points there, you can see what the line, resulting line is. And that's really the thing that should agree between your activity sheet and the one that you're seeing up here. Let's actually do the same thing here. We're looking at a new equation here. It's got something new in it. It's got a fraction, but let's not fear the fraction whatsoever. What are some values that I can plug in for x to make it so that that fraction is going to disappear? Well, once again, if I plug in 0, that whole term will disappear. That's true. But if I plug in a value for 3, what's going to happen? Well, hopefully you can see that if I plug in 3, then 3 times 1/3, that just, those 3's cancel out and I get 1. Or actually, I should say -1, since it's a -1/3 x. So let's try plugging in some values like that here. If I plug in -3 first, then that actually cancels fully out with the -1/3, and a negative times a negative is a positive, so that becomes, that whole term becomes 1. And 1 plus 1 is equal to 2. In the same way, I can try plugging in a value of 0 for x, and that entire term drops out, and I just have y equals 1. And lastly, if I plug in a value of 3 for x, then that first term becomes a -1, and if I add another 1 to that, I get 0. It looks like I could also get this same ordered pair by plugging in a value of 0 for y and then solving for x, and I would get a +3. So I'd get that bottom combination of numbers going in the opposite direction if I plugged in 0 for y. Okay, well, if I plot those points, you can see where those points are. And once again, the line looks like this. So the point of this was taking a look at the equation and asking yourself, what are some easy numbers that I can plug in? In this case, easy meant numbers that'll make that fraction disappear. So do this one using the same techniques here of knocking out that fraction. You probably don't want to put square root of pi in for x for this, although you could do that if you want to do that. But think of the kinds of numbers that you could put in for x so that the fraction disappears. Take some time for that. Welcome back. Well, as you can see, the strategy that I had was to plug in 0 for x and then 0 for y. I got 0, 3 as the first point there. That's our y-intercept. And when I plugged in 0 for y, I got -6 for x. So there was a value of -6 for x. I figured, let's try +6 for x here, and I got another 6 here for y. So that's the third point to the far right there. As you can see, probably any even number for x you could plug in and knock out that fraction of 1/2 there. You could have something that would cancel out with that too. And so hopefully you got a line that is well represented by the one that you're seeing on the screen here. So to review here, an x-intercept is any point that has a y value of 0. You can have an x value of whatever, where the graph intersects the x-axis. So what's the x-intercept of this line that I'm showing you here? Well, it intersects the x-axis at point 3, 0. So A in this case is 3. A y-intercept is the point 0b, so this time the x value is 0 and the y value is, well, something else, where the graph intersects the y-axis. For our particular line here, the y-intercept is at +1. That's 0, +1 for the y-axis. So for the y-intercept, I should say. And so the value of b is just 1. So to find the x-intercept for an equation, simply plug in a value of 0 for y. In the same way, if you want to find the y-intercept, just plug in a value for 0 for x. So let's actually just use a kind of shorthand way of doing this. Let's just do the x and y intercepts, and then once we have those 2 points, let's just connect it with a line and say that we're done here. So let's first find the x and y intercepts so that we can graph the equation. If I plug in 0 for x, then I get 4 for y. If I plug in 0 for y, then I get, well, It's -8/3 for x. That is, what is that? That is 2 2/3, -2 2/3. So you can see kind of where that's going to go. It's going to be a point about there. And so when I connect those 2 points, I have a line that's sloping upward, similar to what you see there. So in the same way, do this equation here in the same way. Plot the associated line with this equation by plugging in zeros for x and y to find the x and y intercepts. Take some time for that. Welcome back. Well, you can see we came up with a y-intercept of 4/3 and an x-intercept of -4. So the ordered pair 0, 4/3, 0, 4/3 is plotted up there, as well as the ordered pair -4, 0. That's the x-intercept. That gets plotted there as well, and you can see the line is plotted that goes right through each one of those points. So in this case, the x and y values, the location of the points, and the line should all agree on your paper with what you're seeing on the screen here. Okay, so let's try this one here as well. I'm thinking that you're going to find something unusual is going to happen here when I try to plot the x and y intercepts. Namely this: if I plug in 0 for x here, then that first term drops out. 4 times 0 is just 0. So I have 5y is equal to 0. Well, if that's the case, then y must just be 0. So what do you think is going to happen when I plug in 0 for y? Well, I'm just going to get the same thing back again here. If I plug in 0 for y, I get x equals 0 once again here. So we've already got that point. The line goes through 0, 0. The x-intercept and the y-intercept are the same thing. They are both the origin. And so I actually need a third number to plug in for x or y in order to find out really what the orientation of this line is. I need to be able to plot a second point, don't I? Well, okay, so I'll plug in 5 for x, and I'm choosing 5 because I'm noticing the 5 and the 5y here. So if I plug in 5 for x, then 4 times 5 in that first term, 4x, 4 times 5, that's going to be 20. And so I'm thinking that's going to divide very nicely when I have to divide both sides of the equation by 5. So I'll get a nice whole number for y. Alright, so if I plug in 5 for x, that first term becomes 20. So I have 20 plus 5y is equal to 0. I'll subtract 20 from both sides. That'll send the 20 over to the other side, basically. And I'll have 5y is equal to -20. So that then, when I divide both sides by 5, I'm going to get y is equal to -4. If I plot that point, it's right there, and you can see that's where our line is now. All right, so do this one here as well. I think you'll find a similar event will occur when you try to find the x and y intercepts, forcing you to make a second point of your choice in order to find what the line is. So take some time for this. Welcome back. Well, once again, we found that the origin was one of the points that is on this line, and so we got the same response when we tried to find the x and y intercept, forcing us to make a second point so that we can find out what the orientation of the line was. And you don't have to choose the one that I chose here, but hopefully you chose one that made it so that you can get a nice even number for y, so that plotting the line was as easy as possible. So let's take a look at what it looks like. We've seen when we plot equations that have both x and y in them, it might be of some value for us to ask, what does it look like when we plot an equation that has x but no y, or y but no x? Well, let's start off with this first equation here. This is y is equal to 3, and this one is kind of peculiar in that if no matter what value I plug in for x, I'm always going to get the same response here for y. -2, if I plug in -2 for x, it doesn't really make any sense here because x doesn't really fit into that anywhere. We're always going to get a value of +3 for y. Okay, so you can see where that point lines up. If I plug in 0 for x, it's once again y is equal to 3, so that's where that point is. And lastly, if I plug in 2 for x, y is once again 3. And that's where that point lines up there. So if I connect those 3 points together, I get the set of all locations in the coordinate system here in which the y value is 3. You can actually confirm that by taking a look at any point on that line there. If you were to ask yourself what are the coordinates of each of those points on that line there, they should all have a y value of 3. So all of those points where the y value is 3, all of those points are lighting up in that line. So plot this line here. Set y is equal to -2, so you can plug in some values for x, and you're always going to get the same value for y there, and then plot those points and see what they look like. Take some time for that. Welcome back. Well, we're now seeing a line that shows all of the points in the Cartesian coordinate system where the y value is -2. If you were to take a look at any of those points on that line, the y coordinate of that point is -2. Those are the points that are lighting up here in that line. You can probably guess here that any line that has that is simply x or y is equal to something, any line that has a y in it but no x, in other words, any equation that is y equals something, y that is y but no x, it's going to show up as a horizontal line, much like this. So see if you can predict what's going to happen when we take a look at equations that have an x in them but no y in them. See what kind of line we're going to be getting with that here. So let's actually take a look at this equation. We're going to graph x is equal to -2. In this case, there's only one value I can plug in for x, isn't there? And it's -2. And as it turns out, I can get a bunch of different values for y. The equation up there doesn't say anything about what y is supposed to be. Y can be whatever it wants, but x has to be -2. All right, so we've got 3 points here that we can plot in the coordinate system to the right here. There's the first one, there's another one, and there's the third one right there. What kind of line is this going to be? Not horizontal, but vertical. So you can see there we are lighting up all the places in the Cartesian coordinate system that have an x value of -2. All of those points are lighting up in that line there. So do this one here. You'll actually have to solve that equation for x. You'll have to simplify it just a little bit, but once you do that, then you should know exactly what number you're going to plug in for x, and then plot the line accordingly. Take some time for that. Welcome back. Well, as you might have predicted, this line is also going to be vertical. It's showing all the places in the Cartesian coordinate system above in which the x-coordinate is 4, which satisfies that equation in the upper left-hand corner there. So it's we can see that in the t-table that was made on the left-hand side here. We can see it in the line that's plotted. So what kind of line do we have when it's just y, our equation is just y is equal to something? We have a horizontal line. What kind of line do we have when our equation is just x equal to something? And I'm just representing the something in both cases with the letter k. So k is not important, it's just the x equals something. When the line is just x equals something, that's not a horizontal line, that's a vertical line. Okay, so let's take a look at each one of these equations here. We've done some stuff with y is equal to something and x is equal to something. Let's come back now to equations that have both x and y in them, and let's examine some of the dynamics of how these equations can be manipulated and how they work and how it has an effect actually when we plot them on the Cartesian coordinate system. I'm taking a look at this equation here, y is equal to -2x plus 3, and you'll see that this equation is in a special form where It contains both x and y, but y is sitting by itself. And you'll see that this equation has got y in it, and it's got an x term in it on the other side and a constant term in addition to that. And so you can see here that this is in what we call slope-intercept form, or y equals mx plus b form here. And you'll see really what that means here in just a moment. If I were to plug in some values for x here, let's say -1, 0, and 1, 0 will be pretty easy here. 0 will give me a y value of 3. Negative 1 will, if I plug that in, it'll be a value of 5, and if I plug in a value of +1, I'll get a value of 1. So if I plug in those 3 points there, and I create my line, I want you to notice something about this line. This line has a y-intercept. We've talked about that before. The y-intercept is where it hits the y-axis. Its y-intercept is 3. In addition to that, I want you to notice that the slope of the line is such that it goes downward. As we're moving towards the right, the slope of the line goes downward. It has what we call a negative slope. And how do we describe that slope? It's how much the y value changes with each change in x. You can see here that as I'm moving to the right by 1 x value, the line actually goes down by 2 x values. The slope of this line is -2. So it's going, because it's going down 2 values for every unit that I'm going to the right. So that's actually the slope. We have a slope of -2, and we have a y-intercept of +3. We'll take a look at the equation here. Y is equal to -2x plus 3. Do you see the slope of -2 anywhere in that equation? Do you see the y-intercept anywhere within that equation? The y-intercept, remember, was +3. Well, hopefully you can see that the slope reveals itself as the coefficient on the x term in that equation here. And the y-intercept reveals itself as that little constant, that little number that gets added on after the x term in this equation when it's in this form, y equals mx plus b. Remember, the y has to be by itself with everything else on the other side in order for us to be able to see what the slope and y-intercept are. You can see here the slope again is -2, and we can see the y-intercept of 3, or more correctly 0,3 here in this equation here. And so you can see here that when we describe an equation as being in y equals mx plus b form, the m is the slope. The m is that coefficient on the x term there. In this case, it's -2. The m is the slope. And the b is the y-intercept. In this case, it's +3. So with this in mind, take a look at this equation here. Y is equal to 3x minus 1, and ask yourself, what's the slope and what's the y-intercept? Now, you already know what to do with the y-intercept. You already know what that is. I haven't really introduced slope very well yet. And again, let me just say that it's for every unit that we go to the right in the x direction, it's how much we go up or down. If the slope is positive, then it's however many units we go up. If the slope is negative, then it's however many units we go down. So the slope is going to tell you how many units to go up with every unit that we go to the right. How many units do we go up? And the y-intercept, well, you know where to plot that. So hopefully you can try to plot this without having to create the t-table and plug in some values. You should be able to go right from the equation here to plotting that line. So take some time to do that. Welcome back. Well, you'll notice there's no t-table listed among the results here. All we had to do in this instance was to notice that this equation is in y equals mx plus b form. It is in slope-intercept form, which means that the slope and the y-intercept are immediately revealed to us. The slope is the 3 that's in the 3x minus 1, and the y-intercept is -1. It's the -1 in the 3x minus 1. So, knowing that this line has a slope of 3 and its y-intercept is 0, 0, -1, let's first of all plot that y-intercept, 0, -1. That's the middle of those 3 points there. And I can plot the next point by going over one value and up. How many? Well, the slope is 3, so I go up 3 units for every 1 unit that I go over. You can see that's how I created the second point to the right there. And so you can see that the slope of the line is 3, so it actually slopes upward, kind of like that. And so the line is actually fairly steep in its slope. You can see that a slope of 3 is pretty steep, but you can see very clearly just how that line is put together there. And we didn't have to plug any values in for x or y. We were able to do this pretty rapidly with the equation in this form. So try it with this one here as well, but notice that in this case the equation is not in y equals mx plus b form. So you'll have to do some algebra in order to get y by itself. But once you've done that, then you will be able to tease out what the slope and the y-intercept are and then graph it pretty easily. So take some time for that. Welcome back. Well, with some algebra here, you were able to put that equation into slope-intercept form. Y is equal to 2x plus 2. And so you have the slope showing up there as 2, and the y-intercept also showing up as 2, or more correctly, 0, 2. So we can plot that y-intercept pretty easily. That's the middle of the 3 points there. And we can plot the next point by going over 1 and up 2. That's our slope there of positive 2. Once we've done that, you can actually make some additional points if you want to, just to continue the line, but you get the idea of what the direction of the line is after you've made those initial 2 points. But your line should look pretty similar to what we've got here, and your values of slope and intercept should be identical to what we have here as well. Okay, so let's come back to this problem that I introduced near the beginning, in which you are comparing 3 different data plans for internet access. And to do this, we are introducing 2 variables defined directly above me, in which x is data usage in gigabytes and y is how much you're paying. It's your monthly fee in dollars. If you recall, plan A was $50 a month up front plus 10 cents for every gigabyte that you downloaded. And so how much is that? So if I plug in some values for x, then I can figure out what the monthly cost would be for each of these amounts of downloads. If I plug in 0 for X, I'm asking how much would the fee be if I didn't download anything, if my data usage in gigabytes was 0. So in that case, the monthly fee would be, you guessed it, $50. But if I downloaded 1,000 different gigabytes, that's 1 terabyte worth of data, how much would it go up? Well, it would be $50 plus 10 cents for each one of those gigabytes there. Well, for 1,000 gigabytes, 10 cents times 1,000, that's another $100. So instead of $50, this is now $150. For 2,000, I'm adding another $100 to the bill again, and so that's $250 there. For 3,000 gigabytes, it's now $350. 4,000 gigabytes, it's $450, and 5,000 gigabytes, it's $550. Now, here's a question. How am I calculating each one of these values? The answer is that I'm starting off with $50 and I'm adding 10 cents for each one of these gigabytes here. So if I were to plug in X into that formula here, the formula for Y is $50 plus 10 cents for every value of X. So 10 cents times whatever X is plus $50, that's the monthly fee. So that little expression there at the bottom describes the relationship here between the data usage in gigabytes and the monthly fee in dollars. So we can describe this relationship here with the equation just to the left of me, y is equal to 50 plus 0.1x. And we can also plot this line here. The line has a y-intercept of 50, so you can see it starts off there at 50. As we're taking a look at this, you can't have a negative account balance when you're dealing with internet downloads. They're going to be charging you something. You're probably not going to be receiving money from your internet provider. And in addition to that, you can't have a negative number of amount of data usage. And so when we're taking a look at this Cartesian coordinate system, we're only looking at the part of the Cartesian coordinate system where everything's positive. So we're only looking at quadrant 1. So in the lower left-hand corner, that's the origin. You can see where 0, 0 is. It's not in the center anymore. It's way over there in the lower left-hand corner. So we're just dealing with quadrant 1. And you can see there where the y-intercept would be. It's just at $50. So that's where that line starts, isn't it? When, with each additional gigabyte of download, you can see that the line goes up. The line has a slope of 0.1. That's how much it goes up for every additional gigabyte. So you can see we've plotted this line here. Let's see what happens when we investigate the second one here. This is Plan B. It's $100 a month plus only 4 cents a gigabyte when you download it here. So let's try some values here for X. If we don't download anything, what's the cost? Well, as you can see, you're going to have just $100 a month. But what if I download 1,000 gigabytes worth of data? Okay, well that's $100 a month plus 4 cents for each one of those gigabytes there. 4 cents times 1,000, that's going to be $40. So 100 plus the $40 here, that's going to be $140. What's it going to be for 2,000 gigabytes of downloads? It's going to be $180. There's another $40 for 3,000 gigabytes downloads. That's $220, $260, and then $300 for 500 gigabytes worth of downloads. So what's the relationship here between X and Y? What am I doing in order to get Y from X? Well, I'm taking the X value and I'm multiplying it by 4 cents, 0.04, and I'm adding 100 onto it. So you can see that's reflected there in that expression, 100 plus 0.04 times X. That's our expression that describes the relationship between the data usage in gigabytes and the monthly fee in dollars. And we can plot that line here. That's the gray line here. You can see way off in the left-hand side there, the y-intercept is 100. It starts off at $100, so it starts off being more expensive than Plan A. But as you can see, as you download more and more information there, it starts to become a better option than Plan A. Then lastly, let's take a look at Plan C, which is only $200 a month. And so if I were to take a look at all of these possibilities for data usage, 0, 1,000, 2,000, and so on, you can see that it doesn't make any difference what the value is for X. Y is always going to be the same value. So the equation for this data plan is actually just Y equals 200. And what kind of line is that going to be? Is that going to be horizontal or vertical? Well, it's going to be horizontal here. As you can see, that's the yellow line going across there. It starts off being far more expensive than either one of those other plans, but eventually it becomes the most economical plan as you start to get into 3,000 and 4,000 gigabytes of downloads. So you can see here that we've actually defined 3 separate areas in which different plans are the best plan. So I'm looking at the orange line here, that's Plan A. From 0 up to about 900 gigabytes or so, that's the cheapest plan. It's the one that's closest to the bottom, the lowest fees, isn't it? It's below the other 2 lines, and so that's the cheapest plan. But from about 900 gigabytes of downloads up to about, looks like about 2,600 gigabytes of downloads, it looks like Plan B, which is in gray, is actually the cheapest plan among the 3. And then there's a third region above about 2,600 gigabytes in which Plan C is the best option to choose there. So depending upon how much you're planning on downloading, what kind of lifestyle you have with the internet, you can choose the best plan accordingly based upon the information that you can get when you take these relationships, quantify them, and place them into a graphical format. Something else to keep in mind here is that when we are describing these patterns using 2 separate variables, oftentimes one variable can be described as the cause and another variable can be described as the effect. In the previous example, the amount of downloads in gigabytes, that was really the cause, and the effect would be how much you're having to pay for your monthly fee for your internet service. And so we usually describe the variable that is the cause as the independent variable, and the variable that describes the effect as being the dependent variable. Usually the dependent variable is represented with a y, and the independent variable is represented with an x. Some additional vocabulary that we have here, I'm showing you a set of ordered pairs here, 0, 100, 1,000, 140, 2,000, 180, 3,000, 200, 4,000, 260, and so on and so forth. Any combination of ordered pairs into a set, you can see that I've separated all of those things with commas and placed them inside these curly braces. We have a term for that. We call that a relation. Now I want to introduce a second vocabulary term here, if you will. You'll notice that for each one of those lines that we plotted, for each value of x, there was only one value of y. That was true when we had lines that sloped like this. For each value of x, we only had a single value of y, and it was only a single value of y. We saw that when we had horizontal lines, where a value of x always gave just a single value of y. The only exception to that was when we had when we were graphing an equation that was a vertical line. That was a time in which we could plug in a value for x and we get different values of y. Remember that? We had the t-tables in which we could plug in only a single value of x and we could get wildly different values of y. Those are not as useful for our purposes, and so we tend to define this particular vocabulary term as a function. And simply the idea here is that for every given x, we will get a predictable, consistent y. And that's true for the previous example that we had, where where the data plans are predictable based upon how many gigabytes of data that we've downloaded. If we plugged in 100 gigabytes of data that we've downloaded, we'll get a consistent, predictable value for the monthly fee. That's true for all three of those plans. And so what we're talking about here can really be represented by this picture of a factory here in which a value for X comes in and it goes through that equation there that I'm showing. This is actually the equation for plan B, and the result is that we get a resulting value for Y coming out of the output. So if you can think of these equations as really factories in which we get an input value for X and an output value for Y, then we can describe these things as functions. And the one restriction that we make is that for every value of X, we would only get a consistent single value of Y. And by defining this term called a function, we can actually use this terminology that I'm introducing here in the lower right, where we say that if I plug in 150 into this function, then I'm going to get 106. So what I'm saying here is that if I plug in a value of X for 150, then this function is going to give us a value of 106. So the functional output given 150 is going to be 106. So you can see here this functional notation showing up again above me here. There are two parts to a function, domain and range. The domain is the set of all things that can be inputted into the factory. The range is all the things that can come out of the factory. You might think that in every situation the domain and range should be every possible number, but that's not always the case. For example, if our function that we're using here involves an absolute value sign, then it's possible that the range is only going to consist of positive values. Remember, absolute value makes everything positive, so our range might just be all positive numbers, no negative numbers. The way that we say this is f of x. You can see the picture above me here, f of x, and you can see that above the factory here I'm showing f of x is equal to 100 plus 0.04 x. So this, the way that you place it in this functional notation is simply to get y by itself and then to replace the y with an f of x. It's as simple as that. That's really all it is. And then you're placing it into this functional notation, which is just a different way in which we represent these relationships here. So the domain, once again, are all the things that can come into the factory. Those are all the x values that can come into the function, and the range is all the things that can come out of the function. Those are the f of x's that can come out of the function, the outputs from the factory. So once again, if we, for example, put in 2 for x here, then we'll get a certain value coming out here. I don't think that's the correct value for the output there. I'm just showing a silly example there. The point is that if every input x has only one possible output, y, f of x, then f of x is considered a function. If there is even one instance in which the same input can give two possible outputs, in other words, the same value of x can give two possible f of x's, you can see there I'm showing an example where we put in 2 and we get -7 or 5 coming out. That can happen with some particular relationships. If that's the case, then this is not a function, it's just a relation. So how do we put our equations into this functional notation? You simply solve the equation for the dependent variable y. Y is always the dependent variable, and then just get out your eraser, erase the letter y, and put in f of x, and you've got it. So let's place the following equations here into functional notation. First I'm going to do the one on the left here. Y is equal to 3x minus 1. Well, y is already by itself, so this will be easy. I just erase the y and put in f of x in its place there. I made it into functional notation. For the one on the y, I've got to do a little algebra to get y by itself. 4x minus 2y is equal to minus 4. I pull the x term, the 4x term, onto the other side by subtracting 4x from both sides, and I have negative 2y is equal to negative 4x minus 4. Then I divide both sides by negative 2, and I get y is equal to 2x plus 2. Well, y is by itself now, and I just get out my eraser, erase the letter y, and I replace it with f of x. I place this into functional notation. So in the same way, place these two functions into functional notation. Take some time for that. Welcome back. Well, the first one was pretty simple and straightforward. You just replaced the y with f of x. The second one, you had to solve for y by moving the x term over to the other side and then dividing by 10. You got y is equal to 2 minus 1/2 x, which you could then change into functional notation by simply replacing the letter y with f of x. Well, that's the conclusion of our video here on graphing linear equations. There's so much that we've covered in this video here. We've introduced both the x and the y-axis, and we've talked about the Cartesian coordinate system put together initially by René Descartes. We've plotted some points, and we've talked about how when we're dealing with equations in two variables, that those points represent solutions to those equations. And so we talked about how do we take an ordered pair and see whether or not it's a solution to an equation by plugging that in and seeing if we get a true statement. We then showed how if we plot all of those points that are solutions to those equations in two variables, we can get some interesting lines that have different slopes and different intercepts. We've talked about, I should back up, we talked about the different parts of the Cartesian coordinate system, the origin, each one of the quadrants, 1, 2, 3, and 4. We talked about, coming back here to lines, we talked about the x-intercept of the line, we talked about the y-intercept of the line. That's the places where the line crosses the x-axis and the y-axis. We talked about how when you have an x-intercept, that the y-coordinate is actually 0. We talked about how when you have a y-intercept, that the x-coordinate is 0. We started graphing equations, first by creating t-tables and experimenting by plugging in different values of x and y. Sometimes we've just plugged in zeros for x and y to get the x and y intercept. We plot those points and connect them with a line. We then talked about what happens when we have an equation that has a y but no x, and in that case it's a horizontal line. We also talked about if it's an equation that has an x in it but no y. In that case, it's a vertical line. We went through that process, creating t-tables and plotting points to demonstrate that. Lastly, we talked about placing equations into a specific form that we call the slope-intercept form. That's y equals mx plus b. It's a form of the equation in which the slope and intercept just pop out you, and show you some important characteristics of the line if you were to plot it. The y-intercept pops out, so you can plot that point immediately. The slope defines how much the line goes up or down for every movement to the right that it moves. Lastly, we talked about this new thing called a function. Actually, we first defined something called a relation. Any collection of points, any equation is a relation. All of the things that we've been talking about here are relations, defining different relationships. But when we are dealing with a function, we're dealing with a relation that for any given x only gives us a singular value of y. Only one possible value for y. That was true for all of our equations in two variables that we were working with. All of those things were functions, and you can place those things in functional notation by solving the equation for y and then just getting out your eraser, erasing the letter y, and putting in f of x. That's a tremendous amount of information there. That's a lot that gets covered. This is probably close to a couple of months of high school math that we've covered in just a matter of hours, hour or two, I think. I can't tell what the time is on the camera here, but I'm thinking it's about an hour and a half or so. So take some time, go through your activity sheet, highlight the things that you see as being important. Remember, all of these things are just variations on a single, a limited set of themes, the themes that I've listed here. And so if you understand each one of those themes, then you've got the lesson, and you can apply these same techniques to the homework problems as well as to the exam problems. So take some time to do that, and I'll see you in class.